Welcome back. In this video we are learning few more SIC programs, and this time we are concentrating on input output operations, how they are handled. If you remember, SIC supports three instructions specifically to perform input output operations. The three instructions are TD, RD and WD. What is TD? It is test device. RD is read data from the device, and WD is write data to the output device. Okay, now what is the job of this TD instruction? What is the job of this TD instruction? It will test the device readiness. Test device readiness. Based on the readiness, it will set condition code. Condition test device can be either ready or it can be busy with some other job. When device is ready, condition code will be set as less than. When device is busy, condition code will be set as equals. So if you want to perform read or write operation, prior to that, first you have to test the device. Only if the device is ready, you can proceed with either read operation or write operation. Otherwise, you have to test the device until the device becomes ready. With this basics, let us jump to the program. Let me clean the screen first. Well, now what we are trying to do is, let us assume that we have an input device which is named as in device. One more thing we need to remember here, all the devices, all input output devices, they will have a unique 8-bit code that identifies them. I can say that all input output devices have got a unique address, and that address is going to be represented as 8 bits. Okay, and this address or the unique code, they are represented in hexadecimal notation always. Okay, now coming back to the program, let us assume that we have an input device. And let us say this device ID is F5. This is my assumption. This is a hexadecimal number, 8 bits, F5. Okay, from this device I have to accept 1 byte of data, and I have to store it in a memory location called as data. I have to take 1 byte from this device. I have to store it in data. How much? 1 byte. Then there is another device. This is an output device. Let me call this device as out DEV. So this will also have a unique 8-bit ID to identify it. Let me take this ID as 08. This is the 8-bit ID of the output device. And whatever is present in this memory location data, that has to be given to the output device. We'll accept 1 byte from an input device, store in the memory. From memory, we will send that 1 byte to the output device. As simple as that. But I told you, we can perform input read or output write only when the device is ready. If device is not ready, we have to wait until device becomes equal ready, right? So how to test the device readiness? We have an instruction TD. Which device we are testing initially? It is input device, right? If device is not ready, then CC will be equals. If device is not ready, we will test again. So I will write something like INL. INL is a label. That means if device is not ready, I will go back and test the device again. Device not ready, go back, test the device again. I repeat this process until device becomes ready. When device becomes ready, I can issue the read command. What is the read command or read instruction? It is RD. Read from where? Read from the input device. Whenever I issue RD, what happens? Whatever you are reading from an input device will be copied into the accumulator. Default register involved in this read instruction is accumulator. So now you have read 1 byte of information from input device into accumulator. Now what is the next job? I have received it. I have copied it into a register temporarily, accumulator specifically. From there I have to move it to the memory. So what is the instruction? Store instruction. Should I use STA? No, it is only 1 byte, so I have to use STCH. STCH. What is the memory location name? Data. Right? Now what is the next set of operations that we have to perform? From memory location to the output device, do I have any instruction directly that can perform this operation? No. Again I have to copy this to accumulator. Then from accumulator I have to copy it to output device. Yes, it is correct that already we are having a copy of it in accumulator, but just to make you more clear, I again load the data from memory location to the accumulator, from accumulator back to the output device. This is the set of instruction I am going to write now. So now I have to test the output device whether it is ready to perform input output operation. If device is not ready, how can I know? CC will be set as equals. So if device is not ready, what I have to do? I have to go back and test the device, which I have written here. So I will make a label to this instruction. And this set of instructions will be repeatedly executed until device becomes equal to read the data. It becomes ready, right? When device becomes ready, CC will be less than. So at that point of time, what I will do is I will get the data from the memory location data, 1 byte of data. So instruction will be LDCH. After getting the data into register, I will write it into the output device. So this is the input operation, input 1 byte. This is output 1 byte, right? So now what are the variables we have used here? We have used a device, in device, we have used an output device referred as out device. What are their addresses? I told you they are all 8 bits and we know their values, so it will be byte. They are represented as hexadecimal numbers. To represent hexadecimal numbers, we will use X here. What is the unique identification code of in device? I have given here, it is F5. So it is F5. Similarly, out device is also hexadecimal number. I have given the number, it is 08B. This is just our assumption. You can take any number, but this represents the address of the device. Then what else we have used in our program? We have used another memory data. This is not initialized to any value. This is programmatically initialized. So I have to just reserve word or byte. Obviously byte. How many bytes? Only 1 byte of data transfer we are doing. So this will be 1. Okay, let's move on to the next program. This also is involving the input output operation itself. The objective of this program is hold on. The objective of this program is to transfer let us say some 100 bytes of data from input device. Let us give the input device name as F5 itself. Okay, to memory. Okay, what is the operation that we have to do? We have to transfer how much? 100 bytes. Earlier program we just transferred 1 byte from input device to memory. Now we have to handle a transfer of 100 bytes of data from input device to memory. So what should be the set of instruction that we require now? What is the first instruction? First we have to test the input device. Test the input device. Device not ready. Test again. No need to explain up to this point, right? Then if device is ready, read the data, store the data. Now, how much of data we have transferred from input device to memory? Only 1 byte. But how many number of bytes do we have to transfer? We have to transfer 100 bytes. That means I have transferred 1 byte to an array at the position 0. What is this X value? Initially it should be loaded with 0. Then what I have to do? I have to increment this X value. Along with incrementing, I also have to make sure I have not crossed 100 bytes. Both the operations can be combined in a single instruction. What is that instruction called as? If you have watched my previous video, you will be knowing there is an instruction called as TIX, which will perform two operations. It will increment the value of X by 1. Along with that, it will also compare the value with the variable specified. So what is this K100? It is a variable which I define a constant value 100. What is this data? Data is a memory location which can hold bytes. How many number of bytes? I want to copy 100 bytes here. What is that 0? 0 is a constant word. It has to be initialized with value 0, right? Then if X is less than 100, then I have to go back and I have to accept the next input byte from the device. So I will write, if X value is less than 100, I have to go back to INL. This is the logic of the program. One more thing we have to declare here. What is that? Input device. What is the address of the input device they have given in the question? It is hexadecimal F5. Okay, this program can transfer 100 bytes of data from input device to memory. Thank you one and all. From the next video onwards, we are going to study few programming examples on SIC XE. Thanks for watching.